You can see my screen, right?
Yes.
Okay, great. Yeah, today I don't have much. I didn't get a chance to try and implement it, question number 3. So we'll just go over the reference implementation. And it should be fine. Okay, so in question 3, we have the representation learning using Bygan on MNIST. So they describe what Bygan is down below. This one is for visualizing the data. So you can see it's just, we're just going to use MNIST. Okay, so here's the description of what Bygan is. In Bygan, we have in GAN, we have the generator and the discriminator. So in Bygan, we want to add an encoder. So that you also have a way of sending an image X to the latent code Z. So you have the image, and then you also have encoder that sends it to the latent code. So generator gets latent code to image, discriminator turns image into a single value. The encoder does the opposite of the generator. Right? So it just has to have three modules. And so the change that they need to do here is that so the discriminator must now learn to jointly identify fake Z and fake X. So instead of just sending the image and the discriminator saying, is this a fake image or not? Now it gets a tuple of the image and the latent variable. So it has to determine it from both. It gets to determine it from both. So the discriminator now has to take two things, the image and the latent variable. Yeah, and then we have the fake Z and fake X, and then the real one, and then the encoder's encoded real image. Okay, in the original Bygan paper, okay, and then this is the minimax term. It's almost the same, except we have discriminator has to do X and Z, and then the same here, 1 minus X minus Z. And so X is from the real data, Z is from the encoder, Z is from the latent space, and then this is from the generator. It just, this whole expectation is from the from those. Right. So yeah. So this it should be pretty similar to GAN, but so they didn't give the loss function for the other side, because in let me see, in GAN we have the generator has a slightly different function. They don't give it here. Yeah. Okay, and then there's some architecture things. So yeah, they talk about the Bygan paper, but it doesn't list an algorithm itself. I think it, so in appendix C.1, so if I go to appendix C.1, appendix C.1, there isn't, it's just like discussions here. So I didn't see an algorithm, so I don't think there's any point referencing the paper. So architecture, we'll use MNIST, but the latent variable is from 0 to, instead of uniformly between -1 and 1, it's a normal 0 and 1 with 50 parameters, 50 latent variables. The size of the latent variable is 50. Sorry. Okay, and then some of the hyperparameters. So we have to apply the L2 weight decay. So we have the scheduler, the yeah, to decay the step size alpha linearly to 0 over the course of the training. So just like last time, so we have to use the what they call it. Anyway, we'll see it. It's the way to goes with the optimizer, but decreases the weights over time. We'll initialize the weights using default PyTorch, and then it says 100 epochs. Okay, and then we have to do some extra stuff here. Or I mean, this is the output that we need to do. At least take the first 20 images from MNIST, and then display the reconstruction. So we have to take the images, encode it into the latent space, and then get it generated back, and then reconstruct it for the 20 images. It's okay if your reconstructions are somewhat lossy, so so the utility is there. And then there's this another big thing here that we have to do. So we want to see how good a linear classifier L we can make from the encoded values. So we'll have a linear classifier that takes the latent variables of the encoded and see how good it is. And why is the label? So this is MNIST, so we have the label for the MNIST. Fix E and learn the weight matrix W, the weight matrix for the linear classifier, such that your linear classifier is composed of passing X through E, then multiplying by W and applying a softmax nonlinearity. And then we just use it, using cross entropy loss. And then we also have a baseline so that we have a randomly initialized random encoder with the same architecture. And so then we know, like, we know the difference between a random encoder and a trained encoder, and see how much better it is. Okay. And so we need to provide the following deliverables: the minimax loss function, a loss term over time, 100 samples from Bygan, a comparison of MNIST X images with reconstruction. So we'll take the images, get back to latent, and then back to images. 10 of them. 100 samples is from random latent from 100 random latent space. Test loss plot for the linear classifier on the pretrained. So we need the linear classifier loss over time for the encoder and the random encoder, the trained encoder and the random encoder. Okay, and then the final test losses for the two classifiers. Okay, so I'll just go through the, I have it copied over here to the question 3 reference. Yeah, this is the reference implementation, and we can just go through it. Okay, so we need, the first thing is we need the generator, discriminator, and the encoder, right? So these are the 3 things that's already there. So the generator needs to take in input dim, which is probably, yeah, it's given here. Yeah, it's 50 something, right? It's 50. This is just there we go, latent dim now. And latent dim is latent dim, solvers. Oh, where's latent dim? Sorry, maybe it's default value. Okay, latent dim is 50. Okay, and then 100 epochs, and then the batch size is 128. So we'll start from the input dimension. Then this is just the generator. So 124 batch norm, a couple of ReLUs, and then back to 784. And 784 is the size of the MNIST image, 28 by 28. Well, in the forward, it's shaped back to 28 by 28. Okay, and then discriminator is similar. It just needs to go to one value, and it's sigmoid, so it's a probability. Okay, and then linear, ReLU, linear, bunch of stuff like that. Pretty straightforward. And then encoder, similar. So the output must be the output dim. So the output dim would be the latent variable size, and input dim would be the size of the image. Right, so you have linear, leaky ReLU, linear, batch norm, leaky ReLU, and then back to linear. Okay, so these are the three things. So we have this big solver object that does that takes care of all of these things. Let's see if there's anything interesting. Log interval, batch size. So yeah, these are the loaders. You can want to look at it. It's just a data loader with the batch size. Pretty straightforward here. Look at create loaders. Number of batches in epoch, number of epochs, and the latent dimension. And then it just calls build right away. So we have the discriminator 784, the latent dim. Encoder 784 to latent dim, so it's the opposite of the discriminator, and then the generator is the generator is generates the image. Oh, sorry, this is the opposite of it. I forgot why the ZDim is used. Okay. Yeah, the reason that we need both of these is that the discriminator now has to take the latent variable and the image. So it's just going to be concatenated together. So we have X and Z, and it's going to be concatenated together. Okay, and then we have the atom optimizer with all of these parameters. And then this is a scheduler, so lambda LR. And so this is the lambda. So I think lambda LR means linear regularizer, and then you set how it decays by the lambda, I believe. Know what it, if they say what it is, but or maybe lambda linear learning rate. Sorry, learning rate. So you set the learning rate based on the lambda, and the lambda is that as the epochs grows, then it gets smaller and smaller. And I believe this is the lambda supposed to give you the multiplicative factor. So you set the learning rate from the optimizer, and then it multiplies it after each epoch, or every time you update it, it checks the epoch and makes it smaller, so that at the end it's 0. The last one is almost 0. right? 1 over the number of epochs, whereas the first one is just 1. Okay, and there's the same thing. There's 3 of these. You have to D, G, and oh, there's 2 D optimizers. Okay, I thought there would be 1 for E, but okay, never mind then. And this is our 2 linear classifiers that we have to train at the end of the training. Okay, so let's look at where were we now? So we were sorry, jumping around a lot. Okay, so we have the solver. We create the solver and we did the build, and we have to. So we first do the random encoder training classifier, right? So because instead of doing everything and then resetting the resetting it, let's just get the linear classifier done at the beginning because the encoder has random values on it, right? So this one is, let's look at it quickly. This should be pretty straightforward. This is just a supervised learning. Yep, and where is it? Yep, 0 grad, detach. We have cross entropy, then we do backwards, and then the linear optimized step, right? So we have the Y, we have the prediction, which is the Z values going through it. And this is from the encoder. So you get the image, you encode it, you get the Z values, and then you do a linear classifier on it, right? And then this is just supervised learning. And I don't think there is anything else here. It's just a supervised learning going on. And yeah, and it's detached so that the gradient doesn't go in here, go into. Okay. So we already have the reference losses and the and related stuff for the linear classifier. Okay, and now the next step is to train the big Bygan. And then here we go. This is the big loop train Bygan. Yeah, I don't know what the train modules do, but okay. Maybe it sets it up for training. And so here's the main step here. So we have D, and then this one, we have get the discriminator loss for the D. And the discriminator loss is this same thing we looked at in the problem. So we have the discriminator with the real value. I'm sorry, the latent of the real value and then the actual image, and then we send it to the discriminator, and then let me go back. It's just this equation, right? So we need the log of the dxc and then 1 minus d of xc. So is d of xz and then 1 minus d of xz, and then it's log, and then you take the mean, and then they added half from somewhere. Is there a half here? Okay, yeah, just a constant anyway. So and then so this returns the discriminator loss, and then the discriminator loss is updated from here. Oh yeah, and then one more thing was the and then we have the generator and the encoder update. So they use the same loss, except there's a negative, because the generator and the encoder wants to it has the opposite, right? The has the opposite objective. One wants to minimize it, the other one wants to increase it. So the other thing is that the G optimizer, so when we look at it, so it optimizes both the encoder and the generator parameters. So both of them are added here. So this loop updates both of them, the generator and the encoder. So so it's one-to-one updates, and then after each batch,
So
there's a
Martin, so in a sense, even though they don't have a separate encoder optimizer, it's also getting optimized as part of the generator optimization.
Yeah,
Right?
it's.
So I was wondering why the encoder would not have anything optimized, but it does.
Yep, it's there. The parameters are added to it. So the gradients are calculated and they're updated.
Yeah. So it's just that it's done as part of the generator updates then.
Yeah. It's in the G optimizer. Yeah. I don't know if it'd be possible to have two different optimizers and then have one loss and then have two optimizers run backwards. Maybe you could. I don't know if it would be possible. I mean, it would be possible. Might be messy, but I think this is fine, right? You just give it. You just have the optimizer because they both have the same loss function in the end, right? So you can just have both of them optimized at the same time. Yeah, and I think that's all there is. So that's the main loop. That's the loss function.
And also, as you mentioned, it seems like they just do a single run of the, unlike in some of the other more complicated, maybe because we're doing for MNIST, it's just enough to do a single scan run for each discriminator. Otherwise, generally you would do more of one. Right?
Yep.
Here it's just one-to-one.
Yep. This one, right? So you update the discriminator a bunch of time, and then the generator is updated once, right? But they only do it one time for both of them. So yeah, that's probably it works. So I think that's why they don't worry about it. And so yeah, there's all this code to save it and all of that. So but let's see if there's anything else. So samples. And so this is sampling 100. So you just take 100 random ones. There's some shifting and biasing here. And then you let the generator generate the samples and then turn it into a NumPy. And then you shape it into the image. So you get the samples here, and then you get the training images. So you take the first 20, you reshape it, yeah, all, and then you send it to get the reconstruction. So this is probably the same. So you encode it and then you generate it again, and then you reshape it back. Right, so you use the encoder to turn it into Z, and then you use Z to generate it again, and so you just reconstructing it. Excuse me. Yeah, and then yeah, all this scaling is kind of iffy, but I think it's just scaling it from 0, 1 to negative half to half or something like that. Okay. And so, and then we have the last part where we have to do the solver. So we clear out the solvers, the reset linear. So the linear one, you send it to the GPU, and then you restart it again. And then we do the same again with the train classifier, but now our encoder is trained. And then this is just setting it up. So it we ran it for 100 epochs, and there's 100 images that it created. So over time, this is what it looks like. It does take a while to run through. So okay, let's just jump 6 to 10. And this is just, I think it's just creating samples from the, so at this time it's already good. I think it's pretty sharp. This is working pretty well. And then the results, let me see, this is the start. This is the loss function, and it just keeps decreasing. So very nicely, it just keeps decreasing with training iteration. This is the linear classifier losses. So with random initialization, it does go down, but yeah, because we are training the linear classifier, but it's still not that good. But as you can see, if we have the Bygan encoder, then we have some sort of digit information hidden in the latent variables. So it just shows that there is something in there already that that's pretty easy to figure out from the latent space what digit it is. Yeah, don't know if the 0.5 means something, but probably means it's not perfect. So there's still some loss. Okay, and this was the final samples generated samples. This looks pretty good. And then these are the reconstructions. So the top part is the original, and then I think the bottom parts are the reconstructions. So let's see. I don't know which one is it, the top one or the bottom one, but yeah, the 4 turned into 6. But anyway, so this is the question number 3. So it's, I think, in terms of PyTorch technique, it's pretty straightforward. It's just putting it all together. Any questions on that? Any points to discuss? Yeah, it's the question 3 rough. Okay, so let's just go to the to the collab notebook, and we can just go. There's just a few things that we can we can do. We've already done most of them, so these are already covered in the theory, right? So parts. So we'll just go over them quickly. So here we have this discussion that we had. I believe this image we had at the end. So I'll skip, sorry, to the bottom. If you can remember this from the notes. So this was using forward KL, reverse KL, and Jensen-Shannon divergence, what the fitting would be. So basically it's if we wanted to test it out. I did convert these into okay, so our data distribution is MOG, so it just stands for mixture of Gaussians. And so there's two of them, right? So 0.7, 0.3, these are the weights, means, and scales. And let me run this one. And what happened? Okay, it's running. So we start out with this. There's the plot here. It shows the mixture of Gaussians. This is our data. And then the next one is we have a Gaussian. So a single Gaussian. So if we look at it, let's look at it, a mixture of Gaussians also. So the mixture of Gaussians is, it's just, we do the norm, do the log probability, and then sum it all up. And there's an exponential, but basically we take a mixture of normals with these locations and scales, and then we multiply it by the weights, and then we get these. So there's two Gaussians here basically. So okay, and then the one we want to train is just a single Gaussian. So it's just a single norm with one location, one standard deviation. Okay, and then we do the training of it, and this is also pretty straightforward. So the loss function is we calculate the loss function. We calculate the loss, and okay, let's go to the training part. Sorry, is the loss function is here, and then we calculate the loss, and then we do the backwards and optimize over that loss. So the model is what this is a data distribution. This is what our model is. So we're just calculating the loss function, and then the loss function is it comes from here. So train epochs. Loss function is forward KL, and forward KL is just KL divergence with logs. So you take the excess, which is the all the values in here. We have the data distribution and the model distribution, and then we return the KL divergence of those two. And KL divergence is just the the standard expectation of the what is it, the log of the p divided by q, log p divided by q. So this is all in logs, and I think this is, they can do it in p minus q, and then this p is an exponent because you have to do the expectation with respect to p in the diverse. I can just go back real quick. Yeah, just you have to do the expectation with respect to p, and then you have the log p over q. But then if you take the log of everything, then and then expectation is just the sum over each p. And then if you take the exponent of it, it's e to the p, p minus q. So, right, so this is just the KL divergence. And so we're using the KL divergence as the loss function here, and then we do the training. And then at the end of the training, this is the training loss and the test loss, and this is the graph. As we can see, the KL divergence has to cover all of the space. So even though there's nothing here, it has to cover all of it. And then we discussed this in the lecture, right? So yeah, and then the next one is the okay, let's go back here. With KL divergence is the backward scale, reverse scale, where we swapped the P and the Q. So it used to be P data. Yeah, it's written slightly weird because both of them are P, but it just swapped around. And okay, and so 1B, if I run it, and as you can see, all of this is concentrated on the mode because it only has one Gaussian, so it'll just go. This is the best place to put it, and it has the luxury of being zero, or it has the ability to be zero, even though the data has non-zero values in it when you do the backwards. Right? And so that, whereas the KL divergence can't be zero where the data is non-zero, but this can be. So it's fine with it, and we had the derivation. And the last one is the Shannon Jensen-Shannon divergence, which is this equation, the KL divergence with respect to yeah, and then M is the mixture, half of P of Q, and then you have the KL divergence P to M, and then Q to M, and then half, and all of that stuff. Yeah, and then this does, the results are almost the same. I mean, exactly the same. Let's just have one. What was it? Okay. Yeah, yeah, it's the same. You can see the model is the green one. It's right here. So there's this mixture here that they did, which is just weird. I don't know what this orange mixture is supposed to be, what it's supposed to signify. Because if I look at it, this is the mixture, right? Mixture is half of the model and half of the model probability and half of the data. So it's taking average of both of these. I don't know what that means, but you're taking half the model and half the average. So maybe it just shows
so that would be this M distribution, right?
yeah, the
Which
mixture
is
one.
used in the loss function. I believe it's just to show us what we compare to, right?
Yeah, yeah, because I thought it was a mixture of Gaussians that they had trained, a second one, but obviously it's not. So it's just a half of that. But yeah, so that's one that we already looked at. This was the and I know in the lecture, the presentation, this was slightly off, but here, they all look the same height. So I think it's exactly the same, all the data in GSD and reverse KL. Okay, any comments or questions on this demo? Okay, let's go to demo 2. So this is the this is the non-saturating GAN objective. So yeah, the standard objective is this one with the discriminator only worrying about this part, or the generator only worrying about this part, because there's no G here, so this is we don't have to worry about it. So only this part. And this is the minimax objective, because both of them are sort of symmetrical in their own ways. They're both trying to minimize or maximize the same objective. But you can change it so that the generator is just it is just maximizing this, so that the discriminator can maximize the discrimination. How much the discriminator thinks it's not fake, so the generator can. And then the reason was that the sigmoid, the reason was that if the discriminator got too strong, or if the discriminator was sure, it became sure, then its gradients are going to be 0, and so we can't do anything if this D is, the gradient of D is 0, right? Because the gradient is 0, and so you can't update anything. So the problem of the discriminator could be changed. Yeah, the problem of the discriminator could be changed. So that this was the drawing of so sigmoid, and then the derivative of the sigmoid, log of the sigmoid, and then the derivative of the log of the sigmoid, and then the negative of the log of the sigmoid, and the derivative of the negative of the log of the sigmoid. Still not okay. So I think the idea here is that the gradient is 0 here until x is 0, or here, as you can see, the gradient is 0 in this area, and then in this area it's also flat, but it's but in the other case, there's gradient here, and then there's some there's still some gradient in the lower values of x. So if we switch to this one, then going from log 1 minus sigma to negative log of sigma, we change where the grade 0 part of the gradient is. So I'm still not sure. Maybe someone knows, like what the, I thought the x would signify the z, and so in the negative area it doesn't. It's bad to have. Yeah, it's
at least the way I remember it or try to recall it, Mohsen, I don't know whether it's correct, is the fact that and he says it somewhat in the lecture too, that in the beginning the generator is poor, and if the discriminator is very sure that what it's generating is negative, is fake, then you don't get any gradient going to the generator.
okay.
Which means the generator can't improve and you are stuck, because the generator is poor to begin with, and the discriminator is firmly telling it, that, hey, what you're generating is fake. So how are you even going to improve? So you want the discriminator to provide a gradient at that point when the generator is poor in generating real-like images, because in the beginning it doesn't generate real-like images. Right?
Okay.
It'll only start poorly, and when it does that, you don't want the discriminator to be very confident that it is fake, because then the generator will never learn.
Okay, yeah, that makes sense. So at first it's very negative because I know it's fake, and then the sigmoid is supposed to clear it up into, yeah, okay. So then it's mostly in the negative area at first. So here, the negative area, there's gradient in the negative area. Once it's in the positive area,
So,
okay, that makes sense. So I think it's just plot.
so that's at least the way I try to recall it or remember why, you need this non-saturating part. I mean, it's equally true when the generator gets very good, but I think you'll never get off the ground is the easy way I remember.
Okay, that makes a lot of sense. Okay, thank you. I think this is just plotting the sigmoid, so there isn't any anything significant here. Okay, and so this is from the homework that we looked at last week, and this is also from last week's homework. Right, and then so this is the demo 5. This is we're evaluating samples with the Inception Score, yeah, this is a small. Yeah, do a review of what the Inception Score was. So what you did was you took the classification from a model like I think in their case you can use the Inception model or the GooglyNet model. I think this is the Inception model, and there's also the GooglyNet model. And then you look at the class, so you can give it an image, right? This is the classifier Inception or a GooglyNet, and then it'll give you a probability over all the classes, and then you take the KL divergence of the so there's two terms. So you want y over x to be strong. You want it to be very sure that that whatever object it is, it recognizes it. Okay, there's one object, I'm pretty sure of it. It has to have high y probability, but you also want to penalize it if it just thinks it's the same thing. Everything is like the same thing. So you need it to be confident when it looks at an image, and you also need it to have the diversity of classifications. So it has all. It is these two formulations, right? So high entropy in the different classification does, and then also low entropy on if it's sure or not. If it's not sure, if all of it is equally likely, then this entropy is going to be high. So you want it to be very sure, like this is a dog, this is a cat, but you want the high entropy here so that there's it says it's dog, it's cat, everything, airplane, all of them, not just like it's a dog for everything. So this is the Inception Score, right? Just a review from before. And yeah, and then in this one, they actually have the Inception and the GooglyNet here. And to calculate it, there's a it's stored, so you don't have to train it. So they just load it, and then it's calculated here. You get the predictions, and then you take the excuse me. Yeah, you take the predictions, and yeah, it's the exact same formula, but just in this way. So you take the log of the predictions, and then the log of the mean of the predictions. So this gives you the entropy of the how sure it is of the predictions, and then this will give you the diversity of the predictions. And here's the results. So Inception Score is pretty bad here. It gets much better the more we train, and then yeah, and I think this one has a better one. So true images, generated samples, and bad samples. I think these are true images and these are generated samples. So it works pretty well. And then we have the Frechet inception distance, which is similar to the inception distance, but you instead of looking at the classification at the end, you make sure that the moments of the layers below, you check that the moments of the layers below the classifier are close together. So here, the higher the entropy, right? The higher the entropy, the better the score. Here, the closer, the smaller it is, the closer you are to some feature space, then it's better. So okay, so it's also calculated the same way, and they have the same same curve. Let's see how do they calculate it. So the way to do it is yeah. So they have the forward FID. So let me go back here. So there's the forward that takes you X to the final layer, right? So and then and it gives you the 10 different classes. But in this one, you just remove the last layer. So you do everything except you do all the way to average pool. So then you have, instead of 10, you have 1024. And I see, and then forward FID, where did it go? So yeah, the whole stack is the same, except you what is this one? Okay, this is an Inception. Sorry, this is in Frechet. Yeah, calculate FID, stats, and in this one, when you do the calculate the FID stats, you get the features, and then you take the mean and the covariance of the features. And yep, and there's more experiment with adding white noise. So if you add white noise, then the Frechet inception distance obviously increases because this one, there's more entropy. So it increases because yeah. Oh, sorry.
Yeah, they're comparing that in one case, in case of Inception Score, when the noise is added.
Yeah. Oh, there's something in the chat. Yep. Features are. Yep, Yuri. So yeah, it's the features are from the layer before last. Yeah, the last layer is not added. So it's just copy pasted.
So that's the 1024 more than that's what you referred to, right?
Yep.
1024 average.
Yep. So it's just all the layers before the last one. Okay, and so this is the Inception Score. Sorry, there's the entropy goes down with the white noise, and then with Frechet inception distance, it goes up. but yeah, it goes up like in a more nicer way, rather than just with more white noise. You can still see that the quality is decreasing instead of just saying can't tell the difference at the end. There's more nuance. So yeah, that's all there is. I'm not sure why it's so you do the FID of the input feature, you append it. Not sure where it's being subtracted from. I thought this was G and R, real and generated samples. Okay, so you're supposed to do it difference between the real and the generated ones. Calculate real samples. Okay, here it is. So you do it for all the real ones, you do it all for the samples, and then you subtract it. Okay, this makes sense now. Sum and trace. Trace is the yeah, the standard deviation. Okay. So that's any questions on this one? I think that's all there is. So the this is the Bygan, and we already did this in the homework. This is question 3. And yeah, so
Yeah, how long did it take for the MNIST to run? I was just curious what changes, for example, would be needed to make the Bygan, for example, run on CFAR 10 instead of, because there you would have 3 channels instead of binary. Classes wise, it wouldn't be any different. So it would only be the color versus
I think
black and white, right? The grayscale versus color.
There's also more images inside. Each epoch will take longer. Yeah, I was trying to do number 2 here, and yeah, it's just this is randomly generated. This is just using the first 500 samples. The number 2, I was struggling with it. And this was after like almost 20-30 minutes, or actually 1 hour of training of the entire CFAR 10 for the question number 2. So this wasn't working very well for me, but I just did a CPU version, but then I can run it, and you can see how long one, but this is on a GPU. So okay.
Yeah, I was just curious if you had done it and seen, because that seems like interesting next step beyond MNIST to see whether it would work.
So as you can see, it takes
work, but
yeah. I mean, it takes about 10 seconds per epoch, and we have 100 epochs on MNIST. So you can see, 100 times 10 seconds, 1,000 seconds for the MNIST. So it takes about 15 minutes to complete on a GPU. So CFAR 10 would probably take probably take a lot longer. There's much more samples, and there's color. But I wasn't successful in getting number two to work. So I think the images are smaller.
Slightly bigger, I think, right? Is it 32 by 32 for CFAR? I forget now.
I don't know.
Versus 28 by 20.
Yeah, I don't know. See question number 2. Yeah, I forgot how much it is. 256. I think it's 16 by 16 maybe.
Yeah, as far as 32 by 32.
Oh, it's 32 by 30. Okay. Okay. Yeah, I didn't try it on there, so probably would be a good idea to. But CFAR also has the classes, right? So.
Yeah, but MNIST does too, right? 10.
Yeah. So if you wanted to do the Bygan, on there. But I think question number 2 would answer that question if I had if I'd finished number 2. So, but I didn't get to finish number 2, so I don't know how long it takes. In the CPU,
up here in the code, you see in your code itself, train data 33232.
Okay.
Yeah, but they also use very simple generator and discriminator for MNIST. So there are linear models, like simple MLP. And for something successful on CFAR, you would probably need a convolutional net. And the convolutions are much slower on CPU than on GPU.
Okay.
So it would be probably hard to compare knowing the MNIST because it uses this uses a linear model and it's much faster, especially on CPU, but also the speed up on GPU would be significant for the convolutional models.
Okay. Yeah, I've turned it into the GPU model, so I got it running through, and and I just trained it for one epoch, and it produced these horrible images. So, but I have to turn it into GPU. I haven't done the reference one yet. That's probably pretty fast. Yeah. Any other things we want to discuss? I don't have anything else to discuss.
No, at least I didn't have anything that's pretty. I guess it also shows that other than for the very simple things in GANs, it's really heavily compute intensive, right? To think on any real stuff beyond, or even CFAR 10 begins to be pretty compute intensive, even on probably things like Colab and stuff. So.
Yeah. I think
it's probably the limit.
Yeah, in the other homeworks also, I think it's I didn't do the only done like small ones that just even with CPU it's fine to run. But yeah, I'm not sure. I mean, 10-15 minutes is
thinking, some of the stuff that they show in Bygan or style GANs and stuff like that, it almost seems like for. I'm just curious whether anybody has been able to, without significant compute, do anything beyond CFAR 10 kind of stuff and get anything which requires more than 32 by 32 and 3 channels and all that seems out of reach.
I think the TPU can do it, right? I saw that the TPU can do PyTorch, so.
Yeah, no, that you could try that on Kaggle because Kaggle makes TPUs available. Actually, Colab does too. If you have the Go. But yeah, that's why I was wondering whether anybody knows the limits of what you can do on a personal basis instead of having some dedicated compute that you can tap into what stuff playing with
Yeah,
for example, the CFAR experiments for the VAEs were not too long to run on Colab, and I believe you can do like bigger experiments as well. So obviously not like photorealistic stuff, but I think you can kind of at least do some demos using very moderate compute for this. And as regarding, I don't know about the Kaggle TPUs, but the versions that are available for Collab users are not that great. They are kind of old versions of TPU, and I personally had kind of not a very good experience with the TPU training on Collab, so it didn't run really fast for me. So, but maybe there were some kind of mistakes on my side, but the code that worked really smoothly and really much faster than it would be on single GPU on this V3 TPU, which is available through GCP. It did not run or run really slow on the Collab. I'm not sure. It might also be related.
And were you using PyTorch or TensorFlow?
No, I was using JAX. I guess I tried something with PyTorch as well, and yeah, but I cannot say for sure about PyTorch, but I believe PyTorch is worse, or at least not better than JAX on TPU, because JAX is was designed with this easy parallelization in mind, while PyTorch uses some kind of at least they are the most kind of not designed for TPU among the 3 most popular frameworks, I guess.
Yeah. I've seen at least more people on Kaggle and stuff easily switch to using TPU. Yeah, that's why I was curious whether.
Yeah, so on Collab, the bottleneck might also be CPU. So I'm not sure about that. Maybe if you have on Kaggle, maybe if you have a better CPU, you can use, then it might work better even with older versions of TPU. Because CPU is responsible for the data commute, and that might be a bottleneck in my case.
Yeah, no, in fact, just the other day I was seeing that there is some I don't know the extent of it, but I saw some, like, I forget what it's called, preliminary knowledge thing or something like that for GANs on Kaggle. So I haven't looked into it, but that might be something to look at. Playing with that.
Preliminary knowledge for GANs. What does it mean? It's like you starting from some kind of
there was some GAN.
network.
Yeah, there was some GANs related knowledge. It isn't a competition, but it is something.
This one, right?
Yeah, something like that, right? And so I haven't looked at it. So what does that do? It's just style GAN implementation or something like that. If you can just stay on this and go down a little bit.
Oh, cycle GAN.
It creates paintings of different styles.
I think in especially the discussion part, people publish a lot of very nice nice articles on how to get started. I think there's a incentive, right, that points to do this, but yeah. So,
yeah, and the thing I was curious about was, if you go up, they also talk about using TPUs for that, but it's obviously TensorFlow, right? If there's like a I've seen you can use PyTorch with it, but I don't know how well it works. You do get the old NVIDIA GPUs. I forgot what the name was. Sometimes on the collab, but yeah. Yeah, but I think they also have the pre-trained GANs. So you also do pre-trained stuff. Yeah. This would be interesting to do cycle GAN, because I think the bonus question was about cycle GAN, which I didn't attempt.
If you're interested in cycle GAN, I would highly recommend a lecture and code from Jeremy Howard, I think from a couple of years back in the probably the second part of the course of Fast AI course. And I think
the second version, second part.
Yeah. So he nicely explains the stuff, and I believe there is some work in code for CycleGAN, and probably it is adapted to the current version of FastAI, because that one was on FastAI V1. But yeah, so that's another thing to like reference if you want to implement the stuff yourself in PyTorch. Also, I'm not sure if FastAI added support for TPUs. I believe they haven't yet.
Yeah, that was, he was saying that sometime back, he said that's what they're working on. Linkage with Hugging Face and TPUs. Those were the priorities for FastAI changes, but yeah, not yet, I don't think.
Yep. Yeah,
when the CycleGAN reference.
I don't know what this is. It's a notebook here, but.
I see. This is the FastAI implementation. Okay.
Course version 3 and NBS. I don't know what that.
Yeah. I'll post the link to the actual lecture that Arto is referring to. Yeah, it's a pretty good, as with Jeremy's explanation and code. He does a really good job of kind of taking you through what is important.
It's kind of nice complementary to this course in this case, because in FastAI they mostly focus on the practical details of the implementation and much less on the theory, while in this course you have like the lectures are much more focused on the theory, and then you got to work through the practice yourself. So that's kind of nice thing to look at.
Yeah, I agree. Good way to look at it.
Yeah, and also there's a whole bunch of new new papers on GANs. I think NVIDIA published a paper on GAN, right? So so to go back to Google, GAN faces or something like that on 2020. Let's see. Anytime past year. Yeah, this was achieves AI training breakthrough. I don't know if this is, but they had the newer version of the face generator, I think.
Yeah, there was a paper on StyleGAN 3 that I
Oh, okay.
saw. I don't know whether I posted a link to that.
I think NeurIPS is usually in the winter, right? So I think there's a lot of maybe a lot of papers will be introduced in that conference.
Yeah, I did post StyleGAN 3 link. That's like the latest. That was, in fact, I don't know when the paper was, but this particular reference was almost like just a couple of weeks back. And what the class discussed, if I recall correctly, was StyleGAN 2, which was a couple of years back, and now StyleGAN 3.
Yeah, I think NVIDIA has a lot of investment in GANs.
Yeah, because they are originally the only remaining 3D graphics vendors for hardware, right? So they were very much into graphics. So if you think of, as in the lecture he explains, if you think of the whole GAN or even computer vision as inverse graphics, then the fact that NVIDIA has a lot of graphics expertise, so they have brought a lot of that expertise to bear on what you do with GANs or with any of the computer vision stuff. And so, that combination is what gets them to produce like high quality images, high quality videos, and from a quality and bringing realistic reality and pixel level accuracy and depiction and stuff. They are kind of that combination of expertise.
If we discussed it,
but
I believe the last presentation by NVIDIA, their CEO who presented stuff, was part of the video was generated by like neural net.
Oh,
right. And yeah, I guess it was not kind of like something you, not like indistinguishable, but if you were not expecting, probably you wouldn't have noticed. Yeah, I'm not sure about that because I haven't watched the presentation myself, and now I know that the part is generated, so probably if I will notice, but probably the one who doesn't expect it might haven't even spot the difference. So that's regarding the state of the art and on this.
Oh, okay.
Yeah, that plus I think for talking of combination of graphics and video and ML to generate, I think a week or two back, and there was also research posted on generating realistic video-like, or I wouldn't say video-like videos from just very simple, like 20 slices of pictures. You can generate, people have successfully generated from black and white 20 images taken in something like 1888, in the year 1888, and you can kind of create a 250 slice video from 20 consecutive photographs, things like that, which is pretty incredible. Which means, like, you can go back if you have an album of images of events that happen, and you have like 20 consecutive pictures or even slightly delayed pictures you could almost recreate in video what that would have looked like.
Yep, you posted this this one with Microsoft also has face generation, synthetic face data set. Yeah, okay. And so I think this is the last homework in Collab, right? So this is the last one. So we don't have any more homeworks in Collab. So, so if, oh, there is one more. Okay. There's one more Collab, but there's no homework. Okay.
And it might just be some reference. So next week I'll do the lectures on self-supervised. Yeah.
Okay.
Yeah, that is a field where a lot of stuff have changed probably since when the lectures were recorded, because it's kind of hot research topic right now. It's probably I'm not sure what was covered in the lecture, but most likely there are kind of stronger results, and it would be interesting to see, like, to compare the what was kind of expected. It's high, like about 2 years ago, right? What was the time of the lectures?
Yeah, at least as I started to go through it, it seemed somewhat similar. I haven't gotten through all of it yet, but it seemed to cover what, and again, as you said, it's theory, right? So the principles are kind of the same, but the results, yeah, would be a lot more. And they kind of take you, which I like because it kind of sometimes understanding the history and the evolution kind of teaches you the basics. And so they take you all the way from 2010 to about 2000. I think this one was in 20, so probably 2+ years. But it seemed, at least when they covered it, that it, some of it is also touched on in the Jan LeCun course that a couple of us followed. That one guest lecture from the Facebook guy covered Sinclair, and a few of those. Those are mentioned again here as well. So I think, yeah, the directions are there, but I'm sure more state-of-the-art results and more work has been taken place.
Yeah. So the guy from Facebook was Ishan Misra, and
right.
I say there is also an interesting this machine learning street talk podcast episode with him, that if you have time, I would recommend. He speaks about self-supervised learning in
this one,
image domain. That one is with Lex Friedman. I guess it would be interesting as well. But this machine learning street talk, it's called.
Okay.
And I think they can be a bit more technical compared to Lex Friedman in there.
Okay, this is probably it.
Not sure. Yeah, I will look it up and post the link. I think I was listening. I'm not sure if it's on. Yeah,
okay.
It definitely should be on YouTube, but I was listening it on like a podcast on Google podcast or something. I don't remember it, but
okay, there we go. There's the. Okay, this is interesting. I've never seen this.
Oh, maybe I'm
this
mistaken.
one, right?
Maybe it was some other podcast.
No, it's this one.
Yeah, I mean, do they have an episode with? Oh, yeah, cool.
Yeah, this is the one.
Yeah. Then I recommend it. It was quite interesting to, and they were discussing this quite recent papers like Dino and another one about videos. I'm not sure, probably as dub. Yeah, so this AVID paper. So a lot of interesting topics covered, and that was like touching on the latest results in the area.
Well, that seems like an interesting thing to check out.
Yeah, and I'm looking at, so I have some if is I don't know if it's been done GANs on graph data. I'm sure graph data on GANs. Okay, yeah, there's plenty of that. So I'm looking at a problem that might be useful for work, but but I don't know how this is. Yeah, geometric, there's plenty of them. Yeah, seems like. There's another one. So this is for ICLR.
So you want to try again instead of classic methods for generating graphs?
Yeah. So we have a whole bunch of graph representations of data, and then just need to create small variations of that data. And so maybe again would be a good way to get a bunch of graph and then generate more graphs. So if you have slight variation, it's mostly for testing, because our data will be based on tests based on these on the structure of how things are, and then so we have to if you want slight variations and you want to generate new test cases. So if GAN would be a better way instead of randomly generating something, then which doesn't make sense. Or if you use rule based, then it becomes your rule is restricted by the rules.
So I also saw some like variational autoencoders also probably are applicable to this kind of problem. So you can try both and compare the results. Because I think training autoencoder, if you have a lot of graphs, it would be quite straightforward, and the variational approach can be probably also applied quite easily. So that's another option. And I believe there are some papers on that.
Yeah, okay. I just need to put together put together a proposal and see if my bosses will let me work on it. So but yeah. I need to do some literature review and
cool. If it
Thanks,
goes through at your job, it can also be a kind of nice project for this course, I guess, and so you can combine like two things and also share some interesting insights of what you learn. I'm not sure if you can share like the exact model you trained for your job, but maybe you can at least share what you've learned while doing it, if you will go on with it.
Yeah, I definitely will put together a proposal, but I doubt, I'm sometimes skeptical if anyone will, if I'll be allowed. But we have we have some people who are good at who do deep learning, but it's mostly supervised deep learning. So yeah, my goal is just to put it together and then see if there's an interest. So you have to put a proposal and then some ideas on how to do it, and if somebody has done it or if it's if it makes sense. So yeah, that's the I can also look at VAEs and autoencoders and see if they would work. It would have to work very well for it to be useful to the company, but but I think that but I don't do deep learning at work. I just do software engineering, but I'm looking to make some proposals, and sometimes they might be say, yeah, this is interesting. You can have 1 month or 1.5 months. You can investigate this, and maybe people will help you out, and so that might be a good thing. So I'm hoping it would work.
In fact, as Atu said, it that would have been like a project for this class.
Yeah.
Ideal project for the class.
Yeah, but I'm just afraid it won't work, or it will do weird things. So yeah, so that's why I have to make a plan saying, well, I'll do 2 weeks of it, and then I'll know if it's good to go forward or not, or maybe 1 month, and then instead of abandoning my current duties and saying, well, I'm just going to do this, and then after 3 months or 4 months, I'm going to tell you what happened. So they're not going to be happy with that. So yeah, so I'll I got some work to do on the making the proposal, but I think there's enough stuff here. People are doing these things. Oh, there's a.
I've sent another link to Graph RNN paper. Maybe it will be relevant as well.
Okay, great.
In the chat.
Okay. Multi-regression models. But this is for work. So if other people want to do the Kaggle one, or these things, then I'd be happy to participate in a hackathon or something like that. Even though, it's a little bit. I'm sure everybody's very busy, but anyway. But if anybody does any projects or interesting things, then they can submit. And if this is, I think, very much targeted to TensorFlow. Prizes, TPU star or something like that.
Yeah, it's already ended, but I was just because the
Oh,
data is available and
okay.
It's but I just thought it's something different with data, and I was curious about the question, right? Of if we use TPUs, how much does it speed up, and how much does it increase the size of images that we can play with, and things like that. So this would be interesting from that perspective. And it may also be interesting to try PyTorch on TPU, because you could potentially do what Ato was suggesting, which is, take the code from Jeremy's FastAI, which is a little bit dated. It might need to be updated for FastAI version 2, but he might also have, I haven't checked, GANs for the latest FastAI version 2 version as well. I haven't checked into it, but then it's just a matter of taking that code and seeing whether that can be run on the TPU, and how hard or easy it is to do. I do know that people have had PyTorch work on TPUs, except I do believe also that TensorFlow is easier to get running on a GPU than what I've seen Candle folks. Even a couple of people I've worked with.
Accelerate library from Hugging Face, which is kind of make PyTorch more like JAX in terms like you just use accelerate for putting on device, and then you it is handled automatically. So it's also an option to try.
Yeah, there's a yes, you have to use a separate package or something. I don't know. Yeah, seems to be not easy. But I have GPU, and then until I reach the limitation, I think I'll try on GPU first. But I don't think it's that hard to translate TensorFlow to PyTorch and back and forth. But if it's already pre-trained models, then it becomes difficult, I think.
Oh, you can convert weights as well. So it's it might be like a bit tricky, but it's definitely doable.
Okay. Because TensorFlow has a model zoo or model library, right, somewhere that you can just download. And then, yeah, I'm sure the PyTorch also has the you can download them from the vision models. But I don't know if they have it for GANs or, yeah. But there's this one, this is from the TPU side of things.
Well, at least NVIDIA uses PyTorch and GPUs and probably all the original or most of the original stuff related to GANs is in PyTorch actually. So that's at least my guess about it.
Yeah, and all of the Google research is in JAX. So, and then the production code is in TensorFlow. So it's a little bit of a, like if you look at the Google research code, then it's very hard to follow what's going on because they have all sorts of libraries and things like that they use, which is, I don't know if it's standard, but.
They have this tracks library.
Yeah.
And
yeah. Okay.
What else? Yeah. So that is like not as popular as PyTorch and maybe not as readable because JAX uses this kind of functional approach, which is not quite native to Python, I guess. So it's kind of hacky.
Okay.
But yeah, definitely has its benefits and is kind of fun to explore.
Okay.
Okay.
Yeah.
Great discussion.
Seems like that's we're yeah. So yeah. We'll see everyone in next week then.
Yep. Thanks, Martin.
Okay. Thank you.